learned about how to train the networks using the PyTorch library. Okay, so these two functions are key in the PyTorch library. So when you call load.backward, then this is calculated for every parameters, which is connected to the final loads. We somehow track all the parameters, connected to the final loads L using, inside the PyTorch, this kind of graph structures are constructed when we combine variables with some operator, okay? And in the final, we calculate the loss, okay? So always in deep learning training, the last node is the loss, okay? Are you agree with that? Okay, so from the loss, we can backpropagate to all the parameters of the network sector and find DLD sector for every parameters. Okay, that happens when we call load.backward function. Okay, and also this is already known. This is actually the value we set, the small value like this. So we already know this, and this is the list of all the parameters again. So we all know about this. So when we call this function, then this calculation is happened. Okay, so that's actually the thing happened during training using the PyTorch library, and also we learned about the linear regression, which is the regressor using this kind of linear equation. So the input and output have the linear relationship, then we can use linear regressor. If X and Y data are not in the linear relationship, then if we want to fit those data with the linear regression, then maybe the fitting will not be performed, well, okay? When X and Y data is distributed like this, then we cannot fit this data with the linear equation, with the straight line, okay? So, linear regression is the simplest form, so it is easy, good for studying, but in the real world, there's less data which can be fully explained by the linear regression. Okay, are you agree with that? Okay, so we have to study more complex functions. Okay, this is good for understanding, but not good for real world data processing. Okay, so we learned about that. And we learned about the PyTorch style code. And the last code remained is like this. So we first have to define the optimizer, our gradient descent algorithm, which is this one, right? I already write down this equation too much. Okay, this is the gradient descent rule, but there's S here, but I will explain that why it has S here later. Okay, anyways, this is the function that defines the optimizer based on the stochastic gradient descent algorithm. And here we have to denote our parameter sector and the learning rate epsilon here. Okay. And this optimizer already knows this in the code due to this argument. And at the first step, we have to initialize the gradient as 0 by executing this line of code. And this is the forward rule. By inputting input data X to our network, we can get the prediction Y. And this is the loss function, which is defined here we will use mean square error loss, which is actually the Euclidean distance between the prediction and ground truth. And anyways, we calculate the loss. So this is the forward process that get the final loss given the first input data, okay? And then we can call now the loss step backward to calculate this DLD sector. And then we calculate this formula to update our parameter once. And this is the accumulating the loss is not that, important. So we loop through this for the data, and the parameters are getting smarter and smarter, okay? So actually they are learning something from the data, okay? And I also explained this, the multi-layer perceptron, okay? So this is the algorithm that have multiple layers, okay? So from the type, from the name of the algorithm, you can know they have the multiple layers. And perceptron, that's actually, similar to linear regression. Well, this is some basic operator, okay? So we actually stack this basic linear operator in the multiple layers, okay? And also this basic block could be as somehow interpreted as the neurons, okay? So the brains are having stacked architectures by this neuron. We have multiple neurons to represent some signals in the brain, okay? So because of that, the researchers are inspired to stack this kind of linear operator to constitute this multi-layer perceptron, okay? But in the middle, you have to have this kind of non-linear layer to prevent these goes huge linear equation. So to prevent that, you have to involve this kind of non-linear layer in the middle. So that's actually explained here, and I already explained this, okay? So you have to use some non-linear function in the middle of the linear operator. So actually, this is the multi-layer perceptron. You stack the same linear operator, but with the non-linear layers in the middle. And if you stack multiple linear and non-linear layers, then that is called as the multi-layer perceptron, okay? And this is something I explained already. So to implement that, it's very actually easy. You will have the same training code, and you will have the same optimizer, same definition for the loss function and also the optimizer. But you have different definition for the neural network, okay? Previously, we defined only one line of linear operator, okay, when implementing the linear regression, because it has only this kind of function there, right? But here we have multiple linear and non-linear layers, and we have to stack them sequentially, okay? So here, what it is saying is we will stack multiple layers in the middle of this bracket, okay? We sequentially stack these layers. First is the linear, non-linear, linear, non-linear, okay? So this is the implementation of our architecture, which is the multi-layer perceptron, okay? Are you guys following this? Okay. And this is the data generation part, okay? We will generate 1,000 samples, and we will iterate through 10,000 epochs, 10,000 iterations when training the network, okay? And this is the, data generation part. We will randomly sample the input, we will generate their corresponding ground truth, okay? This is our XY data. Are you guys following this? And then what we will do is we will generate X and Y data here, and we made MLP, the multi-layer perceptron layers here. So here, what we will do is, we don't know, we are assuming that the MLPs are not knowing the exact function here, but here by training MLPs, we will enforce this MLP to mimic this nonlinear function, okay? So that's actually x squared plus 3, right? This function is y is equal to x squared plus 3. I mean, MLP, we will enforce this MLP to mimic this function, okay? Using the same code, we'll operate for that. And you can see, I mean, this is the visualization for the losses accumulated here, okay? And you can see during the training, the loss was quite high at the first iteration, but if the iteration goes, the loss, the difference, distance between prediction and ground truth gradually reduced and eventually goes to 0, okay? And you can see now, you can visualize your prediction with the ground truth here. So given some random x, which is not seen during the training, you can regenerate 5 such new random samples. And then you can get their ground truth using the ground truth function, okay, that can generate this X and Y data. And then you can also input your input data, 5 input data into this net MLP functions we learned. Okay, so this is the function we learned, right? And we will input this random 5 input into our trained network, and this is the predicted value. Then we printed out these 2 sets, and you can feel that their exact values are could be slightly different, right? But their tendency are almost same, okay, right? So, I mean, anyways, these MLPs are mimicking this kind of nonlinear functions, okay? Are you guys following this? Okay. So we are making some AI here, right? Yeah. And this is very simple examples, the MLP and the linear regressor, okay? But now we will train the convolutional neural network, okay? I mean, I already explained this. Between image and semantic labels, we can use any differentiable layers, right? But this kind of convolutional neural network was selected because convolution was differentiable, and also it is frequently used operator for processing the images, okay? So it can well transform the images, okay? So they are used to constitute the CNN architecture, okay? And I previously mentioned that the first part, which are composed of the convolutional layers, they are somehow rule as the feature extractor, and the later part are more likely operate as the classifier, okay? So in the CNN, when we compare with the classical machine learning algorithm, it does not have separated module, and they don't have any, I mean, hand-engineered feature extractor, but instead they map input to the output directly. But the first part tend to rule as the feature extractor, and the later part tend to rule as the classifier. And also the first part, they are composed of the convolutional layers, okay? And they are processing 2D signals, okay? The convolution is the 2D convolution operation, so it is kind of the filtering operation we usually call, and they process the 2D signals, okay? And after some layers, if we apply the convolution operation or the pooling operation, then their dimension, 2D dimension, is gradually reduced. And if we think the signals are somehow adequately reduced in their 2D dimension, we flatten the signals, 2D signals, to the one-dimensional signal. So this three-dimensional signal could be flattened to be the one-dimensional vector. And after this, we we apply the one-dimensional operator, which we learned previously. So actually, these operators are same as the MLP we just learned. Okay. The later part, they are processing one-dimensional signal, and MLPs can do that well. But the former part, we use the convolutional operator as the main operator for processing these 2D signals. Okay, and eventually we map it to 10-dimensional vector because we have the 10 classes in this application. Okay. In this application, we can expect that the input image size is like this. Seeing this architecture size, we can expect that. And the final output, because the final output is 10 dimension, we can expect the semantic classes the number of semantic classes are 10. Okay. So are you guys following this? Okay. So this is the brief review on the CNN, and I will show you how to implement this in PyTorch. Okay. So previously, we used this type of grammar to initialize our network net. Okay. So because the network is rather simple until the MLPs, but in CNN, the architectures are becoming large. So we need actually class definition. Okay, I think most of you are familiar with this object-oriented programming concept, right? The use of the class. Okay, so this class can, be used to make some instances, right? And we have to define some characteristics for such instances here, right? And also, this init is the constructor, which is executed once when instance is first made. Okay, you guys already know this, right? So this is the constructor which is executed once when the instance is first made, and this is some method, okay, for doing some actions for that instances. Okay, so this part, anyways, using the class, we can define our CNN architecture. Okay, and we can define some features which are executed once when initialized. And we also have to define our forward function here. And also maybe we have to define backward, and also we have to define parameter update rule, okay, for each layer, right? But we don't have to do this, as I mentioned before, because the gradient calculation is already implemented in the superclass of the PyTorch. So it is automatically inherited from the superclass, okay? And this backward function is anymore depending on the forward function. It is kind of the automatic calculation algorithm that does not change regardless of the forward function, okay? It is kind of iterative algorithm that approximates the gradient for some forward function. So we don't have to implement it whenever we define the layers anymore, okay? So it is just inherit from the superclass, so we don't have to care about this, Okay, so that's why we don't have to implement backward or parameter update rule, which are the derivative, the calculating gradient part, okay, in our implementation. So the thing we have to do is just defining some architecture and also defining some forward rule. That's enough in PyTorch, okay? So, this part, as I mentioned earlier, only executed when the instance is first made, right? So we normally define the architecture here. In this constructor, we define the initial architecture and all of the parameter sector are randomly initialized. When defining this architecture, this sector parameter for convolutional operator and linear operator, they are randomly initialized. Okay, and the thing we have to define is only the parameter, their dimension. This is defining input dimension, input number of channels in the input. Okay, this is the number of channels in the output, and this is the filter kernel size. Okay, and also we have to specify the stride, and also whether we will use pooling, whether we will use zero padding or not. Okay, so if you search for datasheet for this conv to the function in the PyTorch webpage, you can easily find their argument. Okay, we can only specify their hyperparameters such as input channel number, output channel number, stride, filter kernel size, etc. here. Okay, then the output size, output dimension would be determined by these hyperparameters. Okay, and also max pooling. This is the 2x2 filter. Window size. We have to specify window size and also specify the stride. Okay, the thing we learned during the lecture previous was also used here as the hyperparameters. Okay. And we can also use the ReLU in the middle of the combo layers. And also here, we have to define some MLPs that can process the one-dimensional signal after the flattening, okay? And this is the input channel number, and this is the output dimension, okay? So anyways, maybe this have to be 100, and also you don't have star here. Okay, this is actually, anyways, there's some typo here, sorry. So this have to be 100. So the output channel here is 100, and next time the input channel could be 100, and the final dimension of the output should be, should correspond to the number of class. So we can assume, we can expect the data set used for training this network will have 10 classes. Okay, if we have a different number of classes for the classification, we have to change this number to correspond it to number of classes in the data. Okay, and these self-start layers, this variable is stacking these multiple convolution nonlinear max pooling layers, and self.fc layer, it is also stacking multiple linear, nonlinear, linear layers. Okay, so we are defining actually these two layers. The first is the convolutional layer, and the second is fully connected layers. Okay, and we have to define the forward function here, and this is the input, okay? And then the first, we have to input 2D images to the first self-start layer we defined. And this is the intermediate result for that. And we have to flatten that, okay? We have to flatten that. So previously, there's star, that was the typo. So this is the correct grammar for flattening this out variable. And actually, this is the one-dimensional vector flattened. And we have to input flattened signal to the FC layer. And this is the final, actually the output of this entire CNN architecture, okay? So somehow we have to adjust these hyperparameters to make this X 2D image to fit to our, the architecture, their dimension, okay? And besides that, every layers here are already differentiable, okay? The layers defined in this torch.nn is already they are differentiable. And if we stack differentiable layers, then the entire architecture becomes again the differentiable. So we can use gradient descent algorithm to train all the parameters in entire network. Okay, and you can see the same training code here. Okay, we have same line of code for training the entire network, the net actually, and net is initialized with this class definition. Okay, so this net is now instance initialized from this class. Okay, and we have to define the loss function and also the optimizer, and then use the same code to train this entire CNN. Okay, so yeah, this line of code does not change. But thing is, you have to also load this X and Y data. Okay, that part is actually missing in this code. Okay, we are assuming that we secured X and Y data when writing this code, but I mean, now maybe by the end of September, we will raise the assignment 1. And that is actually making some data using OpenCV and training the CNN architecture using this code. Okay, so you can feel that generating X and Y data, that might be, taking some effort, but actually for implementing the training part is not deviated much from this code. Okay, you can feel like that. Okay, so using very simple code, we can implement CNN architecture and also their training code. Okay. Okay. And next, we will. So now we explain somehow the method. Regression method. So MLPs are also explained in the context of the regression here because their output Y somehow is the continuous value, have the continuous value, and also we learned about the linear regression, okay? That is also the regression algorithm. So for the regression, because the output have the continuous value, so the ground truth is also have the continuous value. So they are, compared as the distance. The Euclidean distance. That's somehow a plausible loss function for training the regression algorithms. But from now on, we will learn about training the image classification network. Okay. So classification, that's the something that predicts some discrete integers like this, okay? And these individual integers are denoting some semantic classes like cat, airplane, and so on, okay? This is the classification algorithm, and you cannot, simply apply the Euclidean distance laws on this final output, okay? You may have different loss function, and I will explain about that, okay? So image classification, as I mentioned, have some discrete classes, and images are assumed to have just one main object inside. And we have to rebuild their class based on these images, okay? And actually this CFA10 dataset, there are 10 classes, and MNIST dataset have also 10 classes, have some digit classification task. And also here, there's some semantic classes. And this dataset, Caltech 101, have the 101 classes, and also ImageNet dataset, which is kind of the largest image classification dataset, have the 1,000 classes. Okay. So, anyways, I mean, this is showing various image classification dataset. Anyways, their task is doing the classification from the image input. Okay. And maybe before explaining about this image classification, I have to explain this logistic regression. Okay. This is similar to, their name is similar to linear regression. Okay. Maybe sometime, maybe you will be confused between these two, but they are different. Linear regression is doing the regression using this linear equation, okay? Logistic regression, that's actually using the same linear function, okay? But at the last layer, they apply sigmoid function. They apply sigmoid function, okay? So in that sense, they are not linear, but they are actually also, they are called as regression, but that actually performs the binary classification. So that's why I'm explaining this logistic regression here before explaining the classification task. Okay. So binary classification means there are only two classes. Okay. Binary classification means there are only two classes, 0 and 1. Okay. So I mean, if this function generate one scalar value which belongs to this range, okay? So sigmoid function, you already learned about the sigmoid function, right? This sigmoid function, their x range is -infinity to +infinity, but their y range is 0 to 1, okay? So because in logistic regression, because they apply sigmoid function at the last, so their y range, their output range are bounded to this 0 to 1 values, okay? And by thresholding this the value, the output value, which may be in the range of from 0 to 1, let's say the output is less than or equal to some threshold tau, then we can discretize it to 0. And if the y is larger than some threshold tau, then we can make it to 1. Okay. And actually, this is the classification. Okay. So I mean, the output in the classification task only have the 0 or 1. The output of binary classification that has to have only 0 or 1, because there are two classes, 0 or 1. When we do binary classification, the final output have to be 0 or 1. Okay. And I mean, even though the logistic regression algorithms final output is have some continuous value, which is from 0 to 1, we can threshold it. We can threshold it by deciding some threshold. I mean, this could be kind of 0.5. Okay? And if the final output, which is bounded to 0 to 1, is larger than some threshold, then we can make it to 1. And if the value final output is less than that threshold, we can make it to 0. Okay, so this is the way used in the logistic regression algorithm. So and this is actually denoting this, right? So this is the linear operator and applying the sigmoid function. And yeah, sigmoid function is can be written explicitly like this. Okay, so this is the output of this logistic regression function. Okay, but the thing is, we have to actually make the output of the linear regression algorithm close to 0 when the ground truth is 0. Okay, and also if the ground truth of the sample is 1, then we have to make their output close to 1. Okay, so during the training, what we have to do is this one. When given one sample, their ground truth is 0, then we have to make their output, this output, close to 0. Okay, close to 0, sufficiently far from this threshold. Okay, sufficiently less than this threshold. If the ground truth is 0, we have to do that. And if the ground truth is 1, then we have to make our final output close to 1, sufficiently far from the threshold. Okay, that have to be done during the training. And this loss is doing that. Okay, I will explain that. Okay, from now on. So actually, these two losses are same. You have to first fill that. Okay, so this is denoting Yn is the ground truth of that sample. N samples ground truth. That's Yn. Okay. And Zn is the n samples prediction from logistic regressor. Okay, so I mean, this one is we will call n samples output as the Zn. Okay, and we will call their ground truth as the Yn. Okay, so this formula is denoting that. Sorry. This formula is denoting that when ground truth of that sample is 1, we will apply this loss. Okay. And when ground truth of that sample, n sample, is 0, then we will apply this loss. Okay. Are you agree with this? Okay. And that actually can be written like this. Okay. So when Yn is 1, this term goes to 0. Okay, right? This term goes, because Yn is equal to 1, this goes 0, so the entire term goes 0. And this becomes 1, so this one only remained. Okay, so that's same as applying this. Okay, and inversely, and inversely, when Yn is equal to 0, Yn is equal to 0, this term goes 0, and this goes 1, and that is actually same as applying this because of this minus sign here. I mean, for that sample, it is same as applying this loss. Okay. And then you have to now know these two loss functions are same. Okay. And then I will explain the individual meaning now. And this is how the loss function looks like. This is how the log function looks like. This is having having 1, 0, okay? Every log function crosses the x-axis when their point is 0, 1. Are you agree with that? Okay. And I mean, Zn, as we defined, their range is confined in this range because they are obtained from sigmoid function followed, apply this operation to input x, and we apply sigmoid function to get z, okay? So their values are actually bounded like this, okay? So Zn should be in this range. Are you agree with that, right? And this is the Ln function, right? And this is minus Ln, so I will redraw it like this, okay? So this is the minus Ln Gn function, right? Okay, and the loss is minimized during the training, okay? Loss is minimized during the training. So, I mean, the graphs looks like this, right? So we will minimize loss. Actually, that is same as saying minimize minus ln Gn, right? And that is same as saying Gn goes to +1. So by minimizing the loss function, which is this one, by minimizing this one, for minimizing this y value, for minimizing the y value of this graph, but we want to somehow, the y values are minimized when Zn goes to 1, right? So when ground truth is 1, we have to make our logistic regressor's output close to 1. Okay. So that makes sense, right? When the ground truth is 1, then our output should become close to 1. Okay. Then we can threshold it to make it, to digitize it to have 1 after, getting the output. And also, I will draw the, this could be explained without drawing the new graph. So when yn is 0, we will minimize this for that sample. And minimizing this is actually same as making this close to 1. And that is same as making Zn go to 0. Okay. So when ground truth is 0, we will make our output Zn for that sample goes to 0, close to 0. Okay. So it makes sense, right? By applying this, we can make Zn go to 1. When ground truth is 1, we will make our final output close to 1. And when the ground truth is 0, then we will make the sample's output go to close to 0. And then after that, we can threshold this output to, digitize it. When the values is close to 0 and less than some threshold, we will make it to 0, digitize it to 0. And if the values are larger than some threshold, we will digitize it to have 1. Okay. So this is the logistic regression that can perform the binary classification. And the loss functions are not Euclidean distance anymore, okay? We are not closing the Zn with 1. We are not closing Zn to 0, okay? Because this is somehow the classification task. Okay. So when implementing this logistic regression, actually we will use this iris data set, and in Python, that's very thankful because they already implemented this kind of data loader. So when calling this one line of code, you can get some iris data set, which is very famous. So the thing you have to do is just use that, okay? So we will use first 100 samples. So this is the data and this is the ground truth. So we will use it and make it floating value array. So we will, this is also the data generation code, okay? And the X is having, I mean, the 4-dimensional vector. X is the input, and that is 4-dimensional vector, and target would be just the scalar value, having either 0 or 1. Because this is the binary classification, the target would have 0 or 1. And this is our net architecture. So here we define the same operator as before, okay? But we need sigmoid afterwards, but we will count it later. Okay, anyways, we define this architecture with the linear operator. And now our loss function is not anymore the MSE loss, not anymore the mean square error loss. But here you can see BCE loss. This is the abbreviation for binary cross entropy loss. Okay, that's actually this loss. Okay. This is called as the binary cross entropy loss. So it is already implemented in the PyTorch, so you can just use this loss. And SGD, that's same as before, and you can use same training code, but there are one difference. During the forward, there are additional one line of code, and what they do is applying. So we define the net as Wx plus b, okay? Just the linear, we define the net with just the linear layer. And after that, we will apply sigmoid by ourselves. You can maybe implement this in different way using the class, then you can define it more easily, okay? But anyways, with this example implemented in this way, and then you can find loss and call loss.backward and update the parameters, okay? So by doing that, you can implement logistic regressor for the iris dataset, okay? Okay, and another thing is there could be another loss. This is another loss called as BCE with logit loss. This is some, I mean, trick. I mean, not trick. I mean, in PyTorch, these two types of loss are already defined. So when you call BCE, this loss assumes you already implement the sigmoid part, but this loss already, I mean, regard your function without applying the sigmoid. Okay, so I mean, this loss assumes your final output is estimated without applying the sigmoid function at the last. So I mean, the net is defined with only Wx plus b, okay? And here we don't have any sigmoid function in the middle, but you can apply only this BCE with logistic loss. And the loss itself has the sigmoid function inside. So you don't have to implement applying the sigmoid by yourself. Okay. Anyways, there are multiple ways to implement this. Okay. I want to just introduce some specialized flows for BC task. Okay. And if you if you print out their loss values, they are actually same. Okay. So their usages are slightly different, but what they do actually is same. So you can use either of these losses. Okay. And next is the multi-class classification task. I have to explain this. So previously I mentioned that I will explain image classification task and then explain the logistic regressor first. But image classification that have the multiple classes, but in logistic regression, they can only deal with binary classification task, having just two classes, okay, 0 or 1. So we have to tackle this multi-class classification task, okay? So image classification, because image classification or other types of classification, they have multiple classes, which is larger than 2. So we have to learn about some algorithm that can deal with multi-class classification rather than doing the binary classification. And for learning that, you have to learn about softmax operation first. Okay. What they do is, I already mentioned that at the end of the network, you may have the probability for, n semantic classes. So in the last layer of the CNN, their dimension corresponds to the number of classes, okay? Because they denote some probability for each class. So are you agree with that? Okay, are you guys following this? Everyone clear? Okay. But the thing is, in the middle of the CNN architecture, these values are sometimes bounded if we use some sigmoid function in the middle, but ReLU, if you use ReLU, it is not bounded. In the middle of the CNN architecture, their values are somehow can have some values from -infinity to infinity, or sometimes maybe have just a positive value. Anyways, they are not bounded normally. Their values are not bounded, and sometimes they can have negative values, but there's no, the probability could not be negative. Okay? There's no negative probability. So somehow we have to transform the intermediate CNN's responses to have the probability meaning. Okay. And that is what softmax layer can does. Okay. So what they actually does is this operation. This is the intermediate layer's output, previous layer's output. And then you will apply this kind of operation on the previous layer's output. Okay. And this operation is also differentiable, okay, and does not affect the training the network, okay. And what they actually does is they first apply the exponential function, and by applying this exponential function, you can secure their output to be always positive, okay. So by applying this exponential, it's always exponential of some value, they are always positive, okay? And also we will normalize it by the sum of all the values. So, I mean, let's say this is the last layers, previous layers output. So this is the previous layers output having multiple channels. Then you will apply exponential for each dimension. You will apply exponential to each dimension. And this means you will sum it. You will sum each one. And each individual one will be divided by their sum. Okay. So this is called as error normalization, usually. So I mean, their sum, their probability, because they are probability, their probability sum have to be 1. Okay. So by doing this, you can secure two characteristics of the probability. Each probability have to be positive, and their sum have to be 1. Okay. And that is differentiable operation. Okay. So softmax that's embedded in the last layer of the classification network to make their final output have the probability meaning. Okay. And now this is the cross entropy laws, which is used to train the classification network. So previously we learned about the binary cross entropy laws, which is used for training the binary classification network. Okay, so now we don't have binary here. Okay, so but even though we don't have this, you can think of these cross entropy laws as the extension of the binary cross entropy laws. Okay, so previously it looks like this: yn multiplied by zn. This could be ln. Okay, it looks like somehow this. Okay, and you can see that this is extension of this. They have similar form, right? They have similar form, and this is the predicted probability, and this is the ground truth vector. Having, if there are C classes, this is C-dimensional vector having probability for each class. Okay, and this is the one hot encoded vector. So this is, let's assume this is C-dimensional vector having all 0 and having 1 for correct classes. Okay, this is that vector, and this is some prediction which have probability for each class. Okay, and we will apply these cross entropy laws. By minimizing these cross entropy laws, we can make Q of X is equal to P of X. Okay. So this is our prediction, and this is our ground truth, having only 0 and 1 here because it's ground truth, and they have continuous value, but their sum for each entry is 1. And by minimizing these cross entropy laws, you can make Q of X close to P of X. Okay. So you can think of this as the extension of binary cross entropy laws towards the multi-dimension. Okay. Then you can understand these cross entropy laws. Okay, so and this might be the last content of today's lecture. So this could be extended like this. Okay, the log, inside the log, we can actually I mean, this same term is plus minus, okay? So this was kind of manipulated like this. For this term, we plus this and minus this term. Then this is plus minus, so that was actually 0 previously, right? But we on purpose plus this term and minus this term, then it can be simplified like this, because these two are somehow merged to this term, okay? This is a simple math, so I mean, you can, if you do px and log q of x minus plus log maybe minus p of x, then it could be simplified like this, okay? Anyways, this is simple math. Anyways, the original cross entropy laws could be extended like this, and these are constant because ground truth that does not change, okay? P of x, that's fixed value, okay? For each sample, we define some constant for each sample. Their ground truth is fixed, but Q is only variable, right? So by minimizing this loss function, actually this term does not change, and only this term changes, okay? And when minimizing this term, this is very famous measure measuring the distance between P and Q. This is actually called as, I forgot the name, sorry, KL divergence. KL divergence. In machine learning, this is very famous measure for measuring these two vector, okay? And by minimizing this KL divergence, this becomes 0, the value becomes 0 when these two values are same. P and Q are same. P is ground truth we defined, and Q is our prediction, okay? So when minimizing this, the Q of x become close to Q of x, okay? Okay. So this is the cross entropy laws. So we apply softmax at the end of the CNN architecture when dealing with the multi-class classification and apply these cross entropy laws to minimize their distance between prediction and ground truth. Okay, are you guys following this? Okay. And this is the implementation. The PyTorch, they are very diligent. They already implemented these cross entropy laws. So the thing you have to do is just call this when defining the laws. Okay. Okay, and the later part, next time we will implement the LearnNet architecture in the PyTorch, which is very famous. Actually, the CNN architecture proposed in 1998. Okay, so we will learn about this. Actually, they are used to classify the handwritten images. Okay, so we will implement it using the PyTorch, training and testing. Okay. Okay. So see you next Monday. Thank you. Let's finish here.